side results that have already been published, but of course the main piece is still going on. So the collaborators include Nima, Carlos, Zizhen, and Zhongshen. And so these are two of my students who are actually participating in different part of the project. So I'll discuss most of them in this talk. So the question that I'm really asking is, so we can start from basically is what S-matrix, the constraint of unitarity on the S-matrix, how does it constrain the low energy effective action and their possible UV completions? Now on the low energy effective action part, of course we know that for a long time that there's a lot of constraints, and most famous is the certain positivity constraints. And from the S-matrix statement, it is that if you take your 4-point, for example, your 4-point interaction, and you look at the 4 limit, meaning that you take t equal to 0, you have an expansion, and for any effective field there, you would have an expansion that is given as a polynomial in S. And in principle, the statement will be that these coefficients have to be positive for this to have even a possible UV completion. And of course, if you think about effective field theory, then what you have is you have these infinite number of higher dimension operators, and they have certain coefficients, and they come in different linear combinations to form these coefficients. And so strictly speaking, it is these linear combination has to be strictly positive. And there's various ways to see this. First of all, you can just derive this just simply from the optical theorem. And the way you do that is these coefficients, you can consider this the 4-element amplitude, since the S-matrix is analytic, and you assume that there's a UV completion where the UV completed S-matrix is continued to be analytic. That means that you can analytically continue this function to be a function in the entire complex S-plane. Once you do that, then the coefficient of these parameters can be just given as a counter integral on this complex S-plane, where the counter is encircling the center. So it's encircling this pole, and depending on the degree of this pole, it picks out which degree of coefficient you have. Now, of course, you can deform the contour to this contour along the real axis and the infinity part. And of course, from the fact that all the singularity or discontinuity of your S-matrix must lie on the real axis, you know that there's the only non-trivial structure along the real axis. So the deformed contour takes this form. And and then usually we have from unitarity you have the Frazel bound, which tells you that this cannot, the amplitude cannot grow too fast at large S, and that guarantees that there's no contribution from infinity. And therefore, you only have this contour along the real axis, and this contour is essentially just picking out the imaginary part of your 4 limit. And finally, all you have to do is just impose the optical theorem, which tells you that the imaginary part of your 4 scattering is related to the cross-section. And this integral then becomes the definite positive integral. And that's essentially the proof that this coefficient has to be definite positive. So this is a non-trivial constraint on the S-matrix. And you can also see this even more clearly if you consider it as, if you assume that your theory is UV completed perturbatively, meaning that the UV complete S-matrix is given, just change color, I guess we can use blue. So if you perturbative completed, then it's even more clear, because then that means that there's some of your some infinite series of some, well, it might be finite. And the coefficients are, so unitarity tells you that these coefficients are positive, where these are, in 4 dimensions, this will just be some kind of Legendre polynomials. There will be some complication if the particles are scattering or have spins, but in principle, in the simplest version, you just have these Legendre polynomials. And you can look at their form. And so if in the 4 limit, then you're essentially evaluating these polynomials near 1. And as you can see, no matter how high the spin, this polynomial, the value near 1 is always strictly positive. And so that means that in the low energy limit, which means S and T is smaller than m squared, which is the UV degrees of freedom, and this is just a sum over positive polynomials in S. And so that's also an easy way to see why the summation, you should have this non-trivial positive constraint. So, okay, so these are constraints from S-matrix for the infrared.
So sorry, what you get constraints that, for which of these coefficients? For all of them or some of them?
So unitarity tells you this is positive. Now these are positive, this is also positive.
So the coefficients of all
the expansion of S is positive.
So the claim is that you take this scattering amplitude, you make the expansion in S, and every coefficient is positive.
Yeah. because you're evaluating the four limits and you're largely in positive S, so these are all bigger than S, which you're looking at the polynomial in this region. And this region, the polynomial is positive. It's just a positive number in this region. So of course, if you go to the negative region, you have sometimes across 0 becomes negative, but near 1, these are all positive. Yeah.
Why does this expression assume that an UV completion exists?
Right, so we're assuming that UV. So that's
No. What is the relationship between a UV completion existing and you being able to write this down? Why can't you write this down anyway?
Right, but I'm just saying that if you have a completion that looks like this, then you can also see that it is positive.
But in general, every theory will look like this, right? Scattering.
Well, okay, so this will be something that I'll discuss later on. Of course, the fact that you're writing simply as a summation over poles means that you don't have polynomial ambiguities here. And the fact that you don't have no polynomial ambiguities is related to that high energy behavior, which I'll spend more time. But that's the other.
Hey, ICTS, please mute your mic.
Okay. So the main part of this talk is really about what about the UV completion itself. So right now we're just talking about the constraints of S-matrix on these higher dimension operators and lower dimension. So let's say we now really want to see, is there constraint that we can say on the UV completion itself? Or more precisely, what about the spectrum of the UV completion? What kind of constraints does the spectrum should generically satisfy? And so, and more precisely, of course, this is a big question, and since it's so big, then the naive answer is no, we cannot say anything really very precisely. So we really want to ask, where do we expect that we can say something concrete? And of course, the first thing we want to look at is perturbative system involving a large number of massive higher spin particles. And so where do these scenarios occur? Well, first of all, it occurs for example, if you want to consider large yin-yang mills. If you want to consider large yin-yang mills, then at a certain limit you would have the bounce.
Sorry, so could you refocus the camera? The camera is not focused on the sides.
Oh, refocus the camera.
The camera is looking at the board right now, so you can't see the slides at all. Thank you.
Okay. So, in one scenario, you have large yin-yang mills. In that case, you would have meson states as bound state, and you want to ask what the meson spectrums are. And of course, if you consider it in the large N limit, then first of all, the meson are bound states that they're not really stable particles. So you really want to suppress their decay processes. Generically, in large N, these decay are 1/n suppressed. So in the large N limit, they can become stable particles, and you can ask such a question. And for me, more interesting is thinking about the completion of gravity. So, for example, if you think about the possible perturbative completion of gravity, so let me just consider n equals a supergravity for simplicity. The 4-point function, let's say if you have some UV completion, the 4-point function will take this form. You have a momentum delta function, you have 16 supercharges. So that means you have this delta 16 supermomentum delta function. And then you have this function f s of t. Now, since this delta 16 cube behaves as energy to the 8th power, so that means that if for the amplitude to be bounded at infinity, we must have this function. So I'm just talking about a function. You must have this function to have a behavior such that when s goes to infinity, this function actually vanishes at infinity. Just f the function itself. I'm taking out the super function, the supercharge piece. I'm just talking about the scalar function. So this will be a candidate completion, and this completion must have this behavior. And just from this statement, you already see that you must have infinite number of higher spin particles. And the reason is that if this is true for a certain value of t, then what you can do is that we can do the complex analysis. And then since since there's no contribution at s infinity, that means the entire complex function is completely captured by the poles on the real axis. So that means that you will have a representation where for some value of t, where the representation is essentially just the sum of S-channel poles on the real axis. However, since this actually gives a faithful representation, that means that this representation should also include actually encode the information of the t-channel poles. And of course, for a finite number of particles, this is not possible because this will just be a finite polynomial. So just from this, you can see that if you assume perturbative completion for this case, for supergravity, you see you need to have infinite number of massive particles, as well as higher spin, which you can show that the spin cannot be bounded using similar argument.
That's a question, I think.
So you don't have a question. Yeah, sorry, I'm a little, just maybe I missed some of the early things you said, but I'm a little confused. As you said, this is perturbative, and in particular, as S goes to infinity, you expect the non-perturbative corrections will be very important, right? Because you don't expect perturbation theory to give you a convergence series, even if it's for any potential supergravity. So why should perturbation theory?
So right now, I'm saying that the perturbative states are completing is. So that means the perturbative states are still coming in the scale is smaller than n Planck. So the gravity itself is still weakly coupled. So so are you talking about the loop corrections to the theory, where the loop corrections become important, and then you have branch cut issues? So
Oh, it was. Never mind.
It'll come back. Hi, Subrat, please.
Sorry, yeah.
yeah, so I'm talking about, so I'm assuming that the perturbative states are coming in while gravity is still weakly coupled. So these states are, so you have these states that are coming in which are smaller than, you can have a scale that is smaller than n Planck. So for example, in string theory, that would be when your alpha prime is smaller than n Planck. Or sorry, 1 over alpha prime.
I see.
Yeah, so I have a separation. So of course, so that's what I mean. Okay, so maybe I should have stressed this a few over here. What I mean by perturbative completion is when gravity is still weakly coupled and these new UV states starts coming in. I want it to be already unitary within this region. For example, usually quantum field theory is already unitary even at tree level. For Yang,
Right,
for example.
Right, so usually quantum field theory would give you something that's formally unitary. All that I'm worried about is that I might have thought that the other terms would become very important in this particular limit as S goes to infinity, and maybe you wouldn't capture that. So let's say you had a very hard behavior as S goes to infinity. Would that, maybe there's some non-perturbative term that actually comes and somehow gets rid of it.
Yeah. Maybe just re-ask Subrat's question. You assume that the amplitude is bounded. And why should the classical amplitude be bounded? Why couldn't it be bounded later on by quantum mechanics?
Because, so maybe I should already include this in the discussion. So already you see that once you have these corrections, actually in the lower energy that corresponds to actually higher dimension operators coming out. And these higher dimension operators will correspond to ideas. Like for example, if I just talk about classical Einstein-Hilbert action I completed in this way, then you will have these R-squared contributions now coming out. And so here, with the R-squared contribution coming out, you already have perturbative violation of causality.
Okay, so you're using causality.
Yeah, so you'll see that there's also a problem there where you need infinite number of particles.
But is there a sharp claim that this boundedness that you impose is a necessary consequence of causality?
That this has to go to 0?
Yeah.
So, okay, so...
And just to add to that, it shouldn't be a sharp claim about the amplitude, it should be a sharp claim about the perturbative amplitude.
About
which may be very different.
About the classical amplitude, because he's just looking at poles.
Yeah,
just classical
amplitude.
Fine.
Yeah.
So is there a clear claim that causality requires this to go to 0 or to have a particular boundedness property?
Yeah.
You can prove this?
I mean, this is Huang's paper that he proved that...
and Huang's paper implies this?
Yeah.
Okay.
So we see that we have these infinite number of states that are required. So in this talk, I'll talk about this in different steps. So first of all, of course, we already know that there's a consistent answer, and the consistent answer is string theory. So I will analyze properties of string theory in the context of this point of view about infinite completion, and that they are strictly, and they satisfy certain constraints, and we'll find that there's some interesting properties of string theory that was previously not appreciated in terms of perturbative string scattering amplitude. And then I will talk about the possible deformations. On the one hand, you can hand-wavingly see why it's hard to find a deformation for string theory from this point of view. But on the other hand, by using what we know, we can actually give you a deformation.
So mute, please.
And we can actually give a possible deformation. And then we'll talk about what are the possible further constraints that needs to be imposed on this amplitude to further constrain these deformations. And finally, I'll talk about some recent results, which looking at this from a different point of view, which is related to conformal CFT Mellin amplitudes and flat space amplitude. And I'll talk about a proof that allows us to actually say that the asymptotic Regge limit, which is basically S greater than T greater than 1, we can argue that the Regge trajectory for theories that satisfy the property that I mentioned before actually has to become linear, which is already, of course, proven by Zohar and his collaborator earlier this year. But so this will be another way of looking at this question. So this is my outline. So first of all, let me just start with string theory and see how string theory accomplishes, because this is actually very interesting. So of course we can think about this completion just as, this is an arbitrary function and it needs to have some vanishing high range behavior. So we can just write it as the most general possible thing we can. We can just write it as a product of poles in the ST and U channel and some function of n that is S and T. Now, what does this function n, S, and T has to satisfy? Well, first of all, it has to satisfy that whenever you're sitting on one of these poles, the factorization has to factorize into something that is local. What that means is that it has to, the resulting residue cannot have any further singularities in the kinematic regime, because this is just a statement of locality. So, but of course you see that this is generically not true, because if you sit on S equals, for example, m1 squared, then you still have all these poles sitting here. And so that tells you that in principle you have all these other singularities that are present. So that in turn...
Does this assume that at any finite mass there's only a finite number of spins propagating?
No, so this is just a general function.
Now, the fact that there is no further singularity. So I understand that at any given S, you get polynomials in T as residues. The degree of polynomial is bounded by the spins of the particle propagating at that mass.
Yes.
Now, if you had an infinite number of spins propagating at a finite mass, it's possible that that could sum up to a singularity in T. Is that inconsistent?
So you're saying that if there's degeneracy and there's a number of particles with the same mass or around,
in string theory, if you fix any finite mass, we do have this degeneracy, but the spin is bounded.
Yes.
Okay, so it's a polynomial of some degree, which is fixed degree, and then of course this cannot.
Yeah, so this, right, so maybe I should, so that means that I'm actually having a further assumption, which is that there's no essential singularities associated with this padding of
And it was, yeah, exactly.
Yeah,
At any given mass, there are no more than a finite number of spins.
Yeah.
Okay.
So this function doesn't have an essential singularities. So, right, so in order for that these, whenever I'm sitting on one of these residues, the final function becomes just a polynomial with no other singularity. That actually implies that this must have a 0 to cancel all of these other singularities that are remaining. So for example, if you have S equals to A for some mass and T equals to B, with some other mass, then that actually requires that NAB must be 0. So this actually tells you that you must have a 0. And of course, because this is STU symmetric, so you have a bunch of pairs of 0 that are requirements for this function and S and T. So essentially, whenever you list, you write a polynomial like this with the poles written out, that actually implies the constraint that there must be vanishing double poles. And this vanishing double poles becomes a very non-trivial constraint on your numerator. So we can try to solve this problem by assuming that our numerator have a factorized 0. So that means that whenever there's a double pole, there's a corresponding factor in your numerator that cancels this double pole. So let's assume the answer is this. If you assume the answer is this, you're done. This is string theory. Okay, so from a functional point of view, string theory is a statement that, from a functional point of view, it's just a statement that these double pole are just the constraint of vanishing double pole is manifest. It's manifest zeros. Okay, so why is this just string theory? Because if you write it in this form, actually the spectrum is then completely constrained to be linear, and we'll see. And this actually is very related to the fact that you're scattering massless particle, and the fact that this masslessness constrains that your spectrum has to be linear. Once you assume that your answer is this, takes this form. And to see this, it's actually a very simple exercise. All you do is you think about, so of course this contains all the massless pole, but we have to make sure that the massless pole has the correct factorization. Now, of course, as we all know, the massless interaction are severely constrained. There's just a few possibilities for massless particles.
Sorry, if you could go back to that slide again. So you want to make sure that if S is mi square and T is nj square.
Yes, there's a corresponding zero.
And I can't. S is mi square. The first factor is mj square. T is mj square. Which is the zero? Is that the u?
So of course, if S and T is this, then it's
then
corresponding to
U,
zero.
right.
T and U is the S, and then S and U is the T. Yeah, so that's what I mean by manifesting.
Yeah.
Good. So we still need to make sure that the massless pole factorizes correctly. And we know that there's only 3 different possibilities of modifying the general 3-point interactions involving graviton and massless states, with at least two gravitons, because it's all graviton on the outside. And that's basically, you have the usual Einstein-Hilbert R, and then of course you can have R squared 5 with some massless scalar, the dilaton perhaps, and you can have R cubed that contributes to this massless interaction. So basically, what that boils down to is that the massless pole can only have this form of residue. You can have a 1/T, which corresponds to the Einstein-Hilbert term, and you can have the constant T's and a term that is proportional to T, reflecting the presence of the R cube operator. But the point is that this is all you can have, nothing else in the massless. And so that means that when I'm sitting, I take the original function, and I take the original ansatz, and I'm sitting at s equals 0, this is the form I get. This has to collapse to something very simple. The fact that this has to collapse to something very simple tells you that all of these terms have to cancel out. So you see that the sum of the mass square has to be identified with the spectrums in the denominator. So in other words, if I have something that is mass, that is m squared, then there's going to be a 2m squared here that requires that there's another particle that is at 2m squared, and so on and so forth. And that tells you that they must have a linear spectrum. Okay. So again, once you've assumed that your solution to the problem of double pole takes the form of factorization, a factorized zero manifestly, you immediately, through the constraint of the massless particle, you immediately find that your spectrum has to be linear integer space, and that's the end of the story. And you find string theory. So this is a very fast. Is there a question?
Yeah. So how are you allowed a 1/T residue?
Excuse me?
Your first residue is a 1/T.
Yes.
Does that have an infinite number of spins in it?
No, I mean, this 1/T is just because you're in a massless kinematics. So massless kinematics are generally singular. So even though you have 1/T, so I think you're saying that, I was saying that when you're looking at a pole, you shouldn't have any other singularities. But because 3-point massless kinematic is very singular, all the kinematic vanish. So generically, some other things are canceled. There's not really a true singularity associated with 1/T.
And you making assumptions about what states are passive, what spins you have in the massless sector?
Right. So, but we know that already in the massless sector, any higher spin particle cannot be consistently coupled to gravity. So it's usually the statement that if you have higher spin massless higher spin coupled to gravity, the 4-point function would involve higher order poles beyond p squared, and then there would be some issues with the material. So then you already know that in the intermediate state can only be scalars or, so you're already constrained. So you cannot have arbitraries. And this is what I mean by, if you look at the massless sector, the interaction is very constrained, and you can actually use this fact to completely constrain your spectrum. Okay. So we plug in this, and lo and behold, we get the type 2b supergravity amplitude. Closed superstring amplitude, which is just a product of these with integer spacing. And interesting, you might ask that, but we have different we have different closed string theories. If you look at the 4-point function, and it's actually a very interesting result. phenomenon, well not phenomenon, but there's a very interesting representation which is completely not at all obvious from the worldsheet point of view, is that you can have this separation where this piece here is a universal piece of the 4 points of the 4-point closed string amplitude, which corresponds to the UV completion of just the pure Einstein piece, Einstein-Hilbert piece. Now for the heterotic string, the reason that you have this extra piece here is just because you have an extra R squared phi operator in the low energy. And for bosonic string, it's just because that you have the R cube operator in the low energy. Of course, there's also an interesting story that you can discuss about why this actually forces you to have the tachyon once you have this R cube operator and doing this perturbative way of completing this. Actually, the fact that you have a universal piece, the universal Einstein-Hilbert completed piece, is not just restricted at 4 points. You can actually go to arbitrary multiplicity. So in other words, for any closed string amplitude, you can always factor out the piece that is just completely isolated from everything else, and that corresponds to the UV completion of the Einstein-Hilbert piece. And for the different string theory, it's just that you have these other pieces coming around due to these other higher dimensional operators. So it looks like you have a low energy theory, and that is described by these 3-point operators, and the UV completion is just completely done separately.
So in string theory, all the solutions have exactly the right number of zeros to cancel the possible double poles.
Yes.
But in principle, you could have extra zeros in the numerator.
Yeah, but if you have extra zero in the numerators, of course you can just tag it on, and then of course what you have is now you would have some different high energy behavior group. And of course, all of these things you have to be consistent with. So this is just a simple argument to see how string theory comes about. But I haven't proved that this is unitary, right? So you have to do this by making sure that it's unitary. And this is what I'm going to talk about. So of course, once we have this, we would like to ask how unique is the answer, and if it's not unique, well, whether or not the 4-point amplitude solution is sufficient.
You have this statement about the graviton scattering amplitudes or the massless scattering amplitudes.
Yes.
Being very similar in the different string theories. Is there an analogy statement for more massive particles? Yeah.
I don't think so. And of course, you can. Even at first case, you already asked that why is it there's 2 superstrings? Why do I have just one function? And the answer is, of course, you're scattering graviton. So if you're scattering different other states, now you can see that the different spectrums now coming in. So
but there's some universal sector, right?
And that's the massless sector. So we're talking about the other.
All the things that can be produced by scattering gravitons. There's some universal sector of that would be the same type 2A, type 2B theory or not?
So anything that can be produced by scattering 2 gravitons, that would require that you have a 2 graviton to this whatever particle state. And I'm saying that this state is universal for 2A and 2B.
Correct.
Yeah.
So now suppose we look at this full scattering amplitude in that universal sector.
Yes.
So these guys can be, the guys who can produce could be arbitrarily massive states, but we only look at those states, not those that are not in the sector. Now I want to know how I put those in external limits. If the claim that with gravitons, all point gravitons, you get something very similar in, let's say, type 2 and heterotic,
Right.
it sounds like by factorizing that statement, you should be able to find some similar statements for arbitrary external states in that universal sector.
At least for the 2 type 2A, 2B, I think that is true. But yeah, that's an interesting statement. I don't know what the answer to that is. So now I'm going to talk about, of course, this was a very fast derivation of the superstring amplitude. We haven't shown that it's actually unitary. So usually when we talk about the string theory is unitary, we go through the no-go state. So I want to rephrase the same thing in the context of just scattering amplitudes. What does it mean for it to be unitary? And of course, so in order to facilitate that, I'm going to consider the center of mass spread. And we're considering, instead of S and T, we're going to consider S, which is related to the center of mass energy and the scattering angle theta. So then you can translate T into a function of S and cosine theta. And the scattering angle now can be decomposed according to what kind of spins you're exchanging using the scattering angle. There's a natural, you can have a natural basis to decompose it. So that's why we want to use this kind of parameterization. And this polynomial that you use to expand your contribution is generally called the Eigenpower polynomial, which depends on D. It has a generating function, which basically you can use this and expand X, and you can get the definition for the Eigenpower polynomials, which for when you have 3 spatial dimensions, you get just the legendary polynomial. Okay, so basically a function that expanded in this Eigenpower polynomial with positive coefficient are basically what we define as positive function, or I mean what people call it as positive functions. So basically unitarity means that all the residues of when you're writing the sum in terms of these poles, the residue has to be positive functions. So that's the statement of unitarity. It has to be a sum over positive function. And as you'll see,
should alpha be d minus 3 by 2?
Oh, here D is the spatial space. Yeah, sorry. Right. So what are the properties? So I'm just going to do a detour for about properties for these positive functions. And once I go to this detour, you'll see that string theory, the fact that string theory is actually positive is very remarkable. Okay, so what do we expect for a positive function? Remember, positive function is defined as an expansion of the Eigenpower polynomial with positive coefficient. Well, first of all, first permutation invariance. I mean, because graviton scattering is permutation invariance, so we already have that this has to be an even function. This has nothing to do with positive. Okay, so first a few statement. If the function is positive in some higher dimension, then it must be positive in dimension lower. This is trivial from a physics point of view, right? Because if it's positive, that means you have a positive expansion on certain spins. When you dimension reduce, the spin decomposes into positive sums of spins in lower dimensions, so the function remains positive. So this is trivial. Second of all, so this is a very important property that we're going to use, is that if this function is positive, then that means the absolute value of R of X has to be smaller than R of 1. Okay, so that means that the absolute value has to be bounded, and this is very simple to understand, because
so R of X was the residue
right.
at any
So,
given point,
yeah,
and X was related to T.
Cosine, it's cosine data, right? In other words, if, right, for example, if Rx has a root at x equals to 1, then that means that this is 0, then this must be a negative function. So if you can show that, if anybody gives you a complicated function, but you just find that it has a root at 1, then this has to be automatically a negative function. Okay? And if we rescale, so this is also interesting, so if we rescale x by a of x, with a bigger than 1, then the difference is also a positive function. And this can be just proven directly just from the generating function that defines the Eigenpower polynomial. We can discuss this if anybody's interested. So these are some useful properties that we're going to use. And if you combine these statements, then you find that if R of x is positive, then the roots of R of x on the real axis must lie between -1 and x minor. And between -1 and 1. So this is just a property.
You're doing R of X as your eigenbars.
Yeah, so that's not the Eigenpower, the expansion of the Eigenpower. And essentially this is just a combination of this, right? Because if there's any root that is outside of 1, then that means that there's something that is rescaling such that it's becoming more positive. So you can rescale it back, but then once you scale it back, then that means the root can be rescaled to 1. But you know that there cannot be a root that is 1 that makes the function a positive. And so that tells you that the root on the real axis must be between 1 and -1. So it's really lying between, any positive function has to have this property. Okay.
And in particular, eigenbars themselves have properties.
Exactly, yeah. So, okay, now we can look at how miraculously string theory is. So of course, the string theory, so here I'm just going to use the open string. The closed string is just a square of this. So you can just look at the open string. If you look at the open string residue, then when you change it into the scattering angle x, or cosine theta equals x, then that has this form. So as you see, that as n is the level, so you're looking at the level n of residue. As n goes to infinity, this is going very, very close to 1. So string theory, the residue is a product of residue, and the residue is as n goes to infinity, the large is going infinitely close to being negative, but it just stops right before turning negative. So string theory is pushing the limit to how you can accommodate all these massive higher, because the higher you go, it does correspond to the residue of these higher spin particles, and it's accommodating that, but and we're still respecting unitary, but in a very non-trivial way. So you see that there's a non-trivial root that is appearing that is approaching 1. Now, so
had that root exceeded 1, it would have been disaster.
it would have been disaster. That means that there's a ghost, essentially, that your theory is non-unitary. And so that means that actually, so the statement that becomes that if you have if you want to prove the no-ghost theorem for string theory from a physical, or maybe I shouldn't say physical, but from the scattering amplitude point of view, that corresponds to proving, so this is not obviously negative, but still that doesn't correspond to a proof that it is positive. So the statement becomes a proof. Is there a proof that exists that such that this product is actually a positive function? And since we started this, first of all, people must have already thought of this in the old days, because people in the old, and when Benny-Zano amplitude come out, this is actually how they try to understand whether to prove whether string theory is positive. And really, this is a very difficult question to ask, even though mathematically this is so simple. It's just a simple polynomial, just asking, prove this simple polynomial to be positive. We tried for a long time, so far we still haven't been able to crack this problem, to actually just prove this mathematical statement, without going through the whole row sheet business and so forth. It's just a statement of how do you prove this is positive. So, as I mentioned, as you go into infinity, you see that this is actually going to the boundary of a positive function. Now, of course, the critical dimension you can already see in this formula. For example, for n equals 3, this is just the polynomial for the level 3 state, and you can extend it on the Gagenbar basis. So, because this is x squared, so you're going to have a spin 2 and a spin 0. The spin 2 and the spin 0 takes this form. For general D, so you see that in order for this to actually match, D has to be actually smaller or equal to 9 in order for these coefficients to be positive. So this already tells you the critical dimension.
Where did you use the superstring? Like in this slide, the first line will work for Bosonic string, right?
No, this is the Bosonic string will be slightly shifted. Right, this residue is for superstring. The Bosonic string will have a different shift factor. It still has a similar form in that it just closes on to close to 1, but it's actually, in some sense, it's not as close to 1 as superstring for a given fixed n level. But still, it asymptotically closes to 1.
The translation to the cosine will be, because it's sort of, if you're thinking of just tachyon scattering.
But if it's graviton scattering, still the coefficient. Okay, so let me just mention another interesting.
Just to clarify, since that came up, is this exactly the residue for tachyon scattering in the Bosonic string?
So you get T plus n.
T plus?
T plus n. Like
Not in fact, so
Yeah, it's not fine. So that's what I mean. It's shifted.
Yeah.
Okay. Right. So let me just mention some other interesting property about this function here. Is that it's actually so this is just a side comment. Is that this is actually a prime, and so you can ask about functions that are prime in the following sense. So let's say you have some positive function. The product of positive function is still a positive function because of just the simple property of Gagenbar. And so you can ask whether or not this positive function is actually a prime in the sense that it's not separable. And indeed, you can show that around the critical dimension of the local critical dimension of this polynomial is actually a prime. It's not separable into 2. So this is just some interesting fact. We were hoping that this paves the way to the proof, but it didn't. But at least not the.
So what is the primeness? I mean, you can already separate this into sum of eigenvectors. You're saying not in product of eigenvectors.
But the products are not positive functions. So the statement of primeness is: can you separate can you write it as a product of positive functions?
And this getting the critical dimension out either through the open string, does it come out as easily for the closed string?
That's a good question. No, it doesn't. Yeah. So there's something very interesting. Okay, so now we can talk about possible deformations. So let's think about the simplest possible deformations. And remember, what really nails down our analysis was the fact that the massless pole cannot be modified, right? The massless pole was very constraining. So the simplest thing, so we go back to our original ansatz, and we can think about, so we have this f function which needs to cancel the double pole. Now we want to modify that f function. So we want to modify it in a very trivial way, and the times some arbitrary function that still we're able to cancel the double pole. So let's say you modify this in this very. Should I stop before?
No, they just keep coming back.
Okay. So let's say you modify this in this fashion, and you see that this gets very problematic because you have to modify something that doesn't mess with the massless flow, and that's STU. So that guarantees that the S channel pole, T channel, U channel massless flow is not modified. So you're not messing around with the 3-point interaction, which is basically fixed in the beginning. But then you see that this factor is proportional to 1 minus x squared, right? So that means this is a negative function. So you have something that is string theory that is which is extremely close to being negative. And if you want to modify it this way, you're just modifying with just a negative function by itself. And you can see that any modification of this form will automatically turns your amplitude to be negative. So this is then the comment about double poles. Even though you can come up with ways to cancel the double pole, it's actually very non-trivial to have something that actually works.
Just to make sure I understood, you're saying that if you want to add something to it, it shouldn't mess with your poles at s equals 0 or t equals 0 or u equals 0.
Right.
The only way to do that is to multiply by STU.
Right.
Times something, and then that is.
In principle, yeah. So of course the assumption is that here the delta is polynomial. Use effect and actually, right. So if you have delta, then this will not work simply because this will just be adding a function that is negative with, well, I mean, as I said, this has a pole at x equals 1, so this is a negative function. And string theory was already sufficiently close to being negative. You're basically pushing it off the cliff. And so if you actually, so in the beginning, we try to do some kind of deformation that looks like this, and we try to do it like a bootstrap, like carving out the space which maintains the H is still maintaining positive. And it always just goes negative easily, and we figured there must be a simpler explanation. It's basically just this explanation that function is already extremely negative by itself. Okay. But does this mean that this is the only solution for the graviton scattering? And the answer is actually no. Because now that we've analyzed what was necessary for positive what was necessary for things to be both positive in the Geigenbauer sense and still respect the massless pole, we find that in the previous case I said that if we multiply STU with any polynomial term, you cannot modify you always automatically turn negative. But so the way out is to actually modify it with something that is non-polynomial. And so by doing this, so instead you're modifying with a term that actually takes away 0. And you can actually understand this term from these zeros and double very easily, because if you're multiplying the STU, that means that you're removing some of the poles. So that means that some of the poles are not necessary. That means that some of the zeros are no longer necessary, right? Because they're not, and then you can just take them away. And indeed, if you just do that, so this is just the stupidest thing you can think of. And actually, it actually works. It actually satisfies all the Geigenbauer positivity condition just using. So I'm just saying that the residue of this new function is actually the residue of an old function, which all of these factors are just positive. So the old functions are positive, then the new function will be positive for the range where epsilon is smaller than 1 equal to 0. So right. So. And actually, I should comment that I'm thinking about in terms of zeros and poles. This is actually very interesting because this also related to a side result where we were able to do this chiral string where we twist so the closed string you can factorize into the open string. So you can think, so the closed string has, the two open string have different sets of zeros and poles. And if you can flip the chirality of one of the open string, actually the zero and the poles actually changes their signature and they actually cancel each other out. And that actually gives you just the field theory amplitude. And so this is just a side comment, so this is related to the scattering equation direction, which you can actually also get from analyzing this. So, so the lesson so far that we learned so far is that the string theory satisfied the positivity in a very non-trivial way. And the reason that it's very non-trivial to find a solution is basically that improved Heinrich behavior appears to be in tension with positivity. Well, what does that mean? Well, that means that, remember that we have this number of poles, this numerator on top, that must satisfy the double pole relation, right? The vanishing of the double pole means that it must have 0 at these double pole positions. So you can actually do a simple count, right? Just a generic count. Every time you introduce a new mass, there's new conditions you're imposing on and that means that the numerator must have sufficient degrees of freedom to to actually satisfy this condition. But that means that the numerator becomes higher degrees of polynomial in SNTU. And you can just count, you can see that the more things you add, the faster the degrees of the numerator run. And in principle, this actually makes your high energy behavior worse and worse. And the way that string theory actually evades this is that in that discussion, there was an assumption which was that the spectrum was arbitrary. The string theory spectrum was not arbitrary, and it's integer space. So that means two integers, it requires the sum of two integers is still an integer. So this degree polynomial growth doesn't happen in string theory. Of course, I didn't discuss it in that fashion because if you look at the masses code, that spectrum, our linear spectrum already appears very fast. But actually, one of the reasons why it's very non-trivial is because there's really a tension about this good high energy behavior and positivity. However, with mass, at least within the masses sector, we've already, as you've seen, we already found that there's actually non-trivial constraints that happen. So now we can ask, does that function, this function here, is this actually a consistent new theory of scattering that is not string theory? Of course, we don't believe that this is true. But how do you see that this is not correct? That there's something wrong. And actually, this happens also in the early days of Benning-Zhang amplitude. When Benning-Zhang amplitude come out, of course, there's this tachyon that's running around. And later on, there was this Lovelace-Shapiro amplitude, which basically shifted the intercept to 1/2 and therefore avoided the tachyon pole. Now, so they have a perfectly fine 4-point function, which, of course, I think, actually, I haven't checked it, but to the best of my knowledge, you can show that it's unitary. But later on, people didn't further study this amplitude, and the reason was because it didn't have a nice 5-point or n-point generalization, so they didn't know what the n-point generalization is. But if you think of it from a particle physics point of view, this is very odd, right? Because let's say you have some 4-point function, and that means that essentially you know all the 3-point interactions from this 4-point function. And in field theory, I can just start building use this 3-point functions to build my higher point functions. So what's wrong? Why does something go wrong? And if you think of it more closely, then you realize that there's the problem is that when you're thinking about particular states on the outside for the 4-point function, you only have information about particular sets of 3-point functions.
Two gravitons and whatever.
Yeah. When you go to higher point, now new 3-point function must come in, which is not captured by the original 4-point function, right? So that means that the possibility is that these new 3-point functions, for those three, they don't have a consistent 3-point function for these other states. So basically, it's just a statement that for 4-point, you're just looking at two states on the outside of some massive states here. But if I look at a 5-point function, then immediately the 5-point function must involve the case where you have a single massive state and two massive states. And this was not captured in the 4-point function here. So, but that also tells you that instead of thinking about what might go wrong going to a higher point, you can still stay within 4 points, but just put the massive states on the outside. So you have a 4-point function, and you have a 4-point function that already tells you what the massive states are. Now you try to construct a corresponding 4-point function when these states are on the outside. And actually, indeed, so this is something that we propose that we're starting to look at as a next step. And indeed, even just looking at string theory, you already see that indeed, when you put the massive states on the outside, you actually see. Remember when I said that if it was just a massless state, what you see is that the polynomial, the Eigenvalue polynomial, is pushing close to 1, right? If you look at the massive states and you compare it to the same level, you see that it's also a product. So the residue is also a product of this cosine theta, and you actually see that one of these products is actually becoming more closer to 1 than the massless state. So in other words, compared to the massive, once you put the massive states on the outside, it's actually becoming even more dangerous than the thing that I just showed you before, for a given n, of course. So actually, this is a non-trivial hint that really we should start, when you're considering both the massless and the massive on our side, the constraint you're getting more and more constrained.
Wait, so this answer that you got is open string, leading Regge trajectory?
Yes. Sorry, what happened? Sure. So let me see, what did I put here? So these, okay, so what I did this is the tachyon state, and these are the three massive states. Sorry, or is it the other way around? Oh, sorry. 3 are the tachyon state, and this is the first higher spin
And
state.
it takes the form just of some shifted Valencia.
Yeah, but shifted not in integer, but with
In terms of x, but in terms of t and SMU, it's just a very simple.
yeah.
Have you done the calculation for 4 spin massive states?
4 spin masses.
For scalars at level 2.
4 scalars at level 2.
All equal mass, but
We've done a few calculations. We've done the first massive scalar is at level 4, right? Because level 1 is the massless, and level 2 is the massive spin 1. Level 3 is the spin 2, but then it doesn't have a scalar. The first scalar appears at level 4, and yeah, we computed that level 4 was yeah. But
did you
is there a particular question? Oh,
Actually,
actually, I don't quite remember what. There was 4 of them. Was just one of them with 3 tachyons.
we can talk later.
Yeah.
These guys have a conjecture for the structure of such amplitudes.
Oh, great. Okay. Okay. So, of course, so this is just still ongoing, and we're still in the process of doing the analysis. But you can also ask, is there some region where you can have definite statement? And of course, since there's summer, we already know there is a particular region where a definite statement can be made. And that's the Regge limit, or the asymptotic Regge limit. Where in the Regge limit, we know that you can define the Regge trajectory, which means that if you have large s and much greater than t with some fixed value of t greater than 1, then we know that the scattering amplitude should take this form with s to the jt. And jt is the Regge trajectory. And one can ask, can we actually constrain theories that have these good high energy behavior, and constrain what the function jt looks like? And this summer we've known that due to Zohar and his collaborator, we know that this jt, you can actually show that this jt must be linear when t is actually greater than 1 as well. So we would like to think of so here I will not review their proof, but I will actually present another alternative version way of looking at this problem, and that is through the relation between Mellin amplitudes and conformal field theories. So of course we know that the 4-point CFT can be written as this reduced 4-point function, and we can now write this reduced 4-point function in terms of Mellin representation, where MST is the Mellin amplitude. And so the game I'm going to play today is that this MST, I'm going to use the relation that this MST has intimate relation with the flat space limit scattering amplitude, and to see why this JT should have this linear behavior. And of course, so just some comments. The presence of these gamma functions is just due. So okay, let me be a little bit sorry. So really, I'm just looking at 4 identical scalars on the outside, so they all have the same scaling dimensions. So the gamma functions here are just there to be reproduce the poles that are necessary for the double trace operators. Okay, for the double trace that involves the 2 phi's and of course their higher twist descendants. Okay. So we can look at the 4-point function, and so the 4-point function, you can write it as an OPE representation. And if you take the u equals 0, v equals 1 limit, when you take it in a way that this ratio is fixed, then this function simply just becomes here, that this is again the Geigenbauer polynomial, and with some u to the delta over 2. So anyway, so just looking at this limit and then comparing with the Mellin amplitude, we can identify what are the poles in the Mellin amplitude. So the Mellin amplitude will have poles in this region, which in order to reproduce this behavior. So in other words, the Mellin amplitude, in order to reproduce all of these behaviors, should have single poles for all the operators that you are crossing.
If you don't mind going back one, I want to make sure I understand that. So that thing that is conformal, you're scattering scalar. I mean, you're taking the 4-point function of scalars.
Yes.
And you're using the form of the conformal block for spin S exchange.
Right.
And that you say to reproduce the structure of that conformal, that known structure of that conformal block.
That tells you that this must have single poles.
Right.
Okay. Now, of course, we know that the reduced 4-point function has crossing symmetry, meaning that if you replace v with this factor, And if you put it related to you put the representation of the Mellin amplitude in here, and you do the exchange of U of E, that just tells you that the MST has to be symmetric in T and MS. So this is very straightforward. But already you see that, of course, that this is very, very similar as a function to what we're looking for. And so what we're going to do is we're going to assume, so first of all, we're going to assume that there is an expansion parameter such that the anomalous dimension of the double trace operator is perturbed. And so that's just to ensure that in the bulk, if you think about it in Witten diagram language, then you're looking at really just tree exchange. And everything else is just 1 over n. And that statement on the CFT side is that there's an anomalous dimension. So because this already gives you the canonical dimension of these double trace operators. So that means that the loop are giving the 1 over n suppressions. If you want to remove it, that means that there's a way to separate the anomalous piece using some parameter. Okay. Now, we can look at the Regge limit, and if you look at the Regge limit of the Witten diagram, then of course it has this behavior. The Mellin amplitude have this structural form, where this is has to some j power, which the j is depending on the spin, and f of t is just some function, but that is just a single point t. So that means that in a large S limit, the Mellin amplitude is represented as a sum over solely pose in t, and plus some polynomial ambiguities. So, but because that you have crossing symmetry, that means that.
Sorry, you didn't ask. I'll slow you down because I'm losing you. Why did we have to go to this Regge limit for what you're saying? Sorry, I probably just missed you. But what I understood is that you said that you needed some poles in the Mellin amplitude. Was that a statement in a particular limit, or was that some exact more general statement?
Sorry, you're saying that it has single poles here?
Yes.
Yeah, this is just general statement.
This is a general statement.
Yeah.
And this is a statement about conformal blocks, so it doesn't make any assumption about large n.
No.
Now, where did large n come to this? Please say that again.
Oh, large n is just that if I think about it from the bulk point of view, then I want to avoid. Wait, where's the large n discussion actually? Oh, here. Oh, on top. Yeah. So the reason that I want large n is because, so I can visualize this as Witten diagrams in the bulk, and of course, since I know that I want this function to later to just go into tree amplitude with scalar exchange, so I want to suppress the loop level.
Yes,
and the loop level is suppressed by 1 over n.
Yes.
And that corresponds, and the reason it's translated into the CFT language, these 1 over n corrections they're correcting these, for example, these double trace operators.
The anomalous dimensions, right.
So I want this parameter so I'm like working backwards. I'm saying that what I want in the CFT. And the CFT is I want these anomalous dimensions to be separable by some parameter.
Right, so in the bulk, in this classical limit, you will only exchange single trace operators. Only exchange particles corresponding to single trace operators. Whereas in the OP from the boundary, you will also exchange double trace operators. I was just wondering whether somehow there is how that plays out. Because from the point of view of the boundary field theory, there are double trace operators.
Right.
And they should also be exchanged.
Right.
Do you club them together with? Do you club double trace and single trace exchanges together somehow? Or is this why you're going to the Regge limit so that the double trace exchanges are not important enough?
I haven't thought about that, but maybe I should discuss later on. Okay, but since this is symmetric, that means that this function can also be represented as solely as S-channel exchange. So that means that if you don't have any polynomial, if the polynomial terms are not important in this, which is maybe related to when does the polynomial term are important, and which is something I'll discuss at the end of the talk. But if it's not important, then this means that this function will have a vanishing large S behavior, with a vanishing rigid behavior. So if the CFT is such that the polynomial terms are absent or not important, then we can say that this function should have a vanishing large S limit. And I'm going to assume that. And in terms of the usual ADS-CFT, this actually corresponds to finite lambda. So in a finite coupling, this actually occurs. Okay, so the claim 1 is that the limit from the correlation function side, which is b equals 1, u equals 0, and I'm taking a large dimension, scaling dimension limit. This actually corresponds to the asymptotic Regge limit of the flat space Mellin amplitude. And so let me just, first I'm going to, and this is particular the region where we're actually interested in. And so we're going to show that why this statement is true. So again, you start with the original Mellin reduced 4-point correlator in the Mellin amplitude form. But of course, since you're taking delta large, but in the limit where delta is proportional to S is proportional to T, they're all large, then you can approximate this integral into this form. Okay, in that limit. And so the statement is that once you write it in a more suggestive form, so remember, so this is just conversion, you can write it in this form. Then you can see that here, so remember this integral is, I should have mentioned this, but the Mellin integral you're integrating along the imaginary axis. So here you have this piece here, where there's an S factor times log V. So in principle, since S is in the imaginary axis, that means a large imaginary S, this is actually highly oscillating. So in principle, this should not contribute. The large S limit is not going to contribute. So naively, you would say that it's not actually contributing. But however, if you take V equals to 1, such that S log V is much, much smaller than 1, then actually the large S limit actually survives. But for not only it survives, because of this factor, because of this factor here, S to the T power, so not only it survives, but for positive T greater than 1, this is actually dominant. So for V, so when V is to 1 limit, so this tells you that when V equals 1, this actually corresponds to the Regge limit of the Mellin amplitude. But there's more, because there's also this oscillating phase for T. And for this oscillating phase, so you can see that the large T limit is actually canceling out. But if U is taking to the limit where at the scale of, or proportional to this ratio, then this entire combination actually, you have a small phase, and this oscillation actually doesn't occur. And actually the large T limit also survives. And that course, and this, because remember delta and T are all going to large, but S is going larger than delta. So that means if I'm taking S to bigger than T and delta bigger than root to 1, then this will be vanishing. So that tells you that U have to go to 0. Okay, so that finished the claims that delta V goes to 1, U goes to 0, and the large delta limit, you get the asymptotic Regge limit. You get the asymptotic Regge limit.
It's like U is the cross ratio or the Mandelstam variable?
Cross ratio. S and T are the Mandelstam. Okay, now we're going to argue that in this limit, the Mellin amplitude has a Regge slope that must be linear. And the proof is, recall that we've assumed this. So since the Mellin amplitude for some fixed T is actually going to 0, so the Mellin amplitude is going to 0. But the gamma functions, so if you look at the gamma functions, it's multiplied by the gamma function. Well, I mean, yeah, there's some, I'm going to, okay, anyway, so, we call it, remember there's a product of gamma functions that's multiplied the Mellin amplitude, which is a function of S. So in large S, obviously the gamma function is increasing. So there's a decreasing factor with an increasing factor. That means that there should exist a saddle point if this is satisfied. And the statement that there must exist a saddle point if this is satisfied actually will show that that tells you that the Regge trajectory has to be linear. And to show that, so basically we just plug in that we know that from the scattering amplitude point of view, I already know that in a large S limit I should take, and in flat space scattering amplitude, in the large S limit, the amplitude should take an S to the JT. So I can just plug this, substitute this into my Mellin amplitude. And so it takes this form. And then I can rotate my contour, because remember, I want to evaluate this near the real axis, so I can rotate the contour. But this rotation is valid because there's no poles on the complex spin. All the poles are on the real axis. So once you rotate it, then you want to say that you want to look for the saddle point. So they can be written in this suggestive form, and so the saddle point for S is basically you just take the derivative of S with respect to this function. And that means that the saddle point is present when this is equal to 0. Now remember, but we're really looking at log V, the V is approaching to 1, and the limit of S log V is smaller than 1 in the previous discussion. So you see that in order for this to even have a solution, T plus JT has to be smaller than 1. there has to be a solution of it. But this has to satisfy this criteria in order for there to be even exist a saddle point. But remember that t, we're looking at t to be large. So if you think of jt as a polynomial, in order for this to even be true, that means that jt has to be linear. It cannot be any higher power than t, because if it's higher order power than t, then a large t, this cannot be satisfied. If it's lower power than t, then of course this t factor is sitting there, and again it cannot be satisfied. And so in this analysis, so using the fact that, or not the fact that if you assume that the minimum amplitude has this good asymptotic behavior, and then you look at that, which implies that there must be a saddle point in your large S integration, then actually connecting this to the flat space amplitude tells you that the flat space Regge trajectory has to be linear. So this is an alternative way to show that the jt, large t, if the amplitude has a split die-off, must have a linear section, which tells you that it has a string. It has, in this limit, it looks like a string theory. Okay. So
it sounded like from your formula that you also found slope of the. You knew jt was some particular number text. Is that right? Or?
But then there's this normalization factor, because these are also with dimension, but then that depends on what your dimension will be. That's why I always write the proportion. Okay, so I've discussed a few topics in this talk. So what are the future, the directions that we're looking at right now? So first of all, of course, in the previous part, we already basically exhausted the massless scattering and the constraints from the massless scattering, which we already found solutions outside of the string theory solution, which satisfies all the possible criteria you could ever ask for a massless scattering. Oh, I should mention that deformed amplitude also have this good asymptotic behavior. So the next step, of course, which I already mentioned, is really we want to now start combining the constraint between massless and massive states. Just we want to put them together and just derive further constraints on these spectrums, these massive spectrums. And it's also interesting that, so we're also looking at numeric bootstrap, which precisely because your amplitude has if it has a good large S die-off, then that means they have a representation in terms of just S channel poles, which through ST duality means that there's equivalent representation for the T channel pole. So you can plug this in, and then you can just assume certain spectrum, and then you can again try to do bootstrap to see what constraints can you derive on the spectrum. So this is also an ongoing project, and so for example, quite straightforward, you can already see, for example, that you cannot have just a single Regge trajectory in the sense that the massive state, it just cannot be a single tower of massive state. It must have daughter trajectories. So you can easily prove that using this numeric bootstrap.
You need the numeric bootstrap for fixed external particles?
Yes, fixed external. So right now we're doing the numeric. So right now we're doing the numeric bootstrap for massless scattering. Yeah, because we think that that's the place where we should have finite most constraint. And actually, it's the interesting question, of course, in showing that there's this linear region for J of T, I had to assume that the Mellin amplitude has this vanishing asymptotics. Now, of course, we can ask what kind of CFT has that behavior. And I think that's and so that would correspond to thinking about what kind of CFT actually has a string related to have a string dual. And I think that we can actually answer this question. For example, we can think, again, we go back to the original Mellin amplitude form. And let's say I want to probe large S. So if you want to probe large S and relative to T, what you can do is you can isolate this Mellin integral along the poles of your gamma function. So for example, if I take S equals to 2 delta plus N, and T equals to 2 delta, so that means that I will be looking at a large, and I'm taking N to be large, such that S is much larger than T. Because once I'm localizing on these two poles, and this is just substituting it there, then this integral is just given proportional to this factor, where these are just you're just taking the residue of these gamma functions, and then you can just take it into the large limit. So taking it into the large limit, and then this is what this corresponds to. Is you're looking at the OBE of you have 4 primaries on the outside, single trace primary. With exchange a double trace, where the double trace has large spin, because the spin corresponds to the large end. So in this larger limit, you're really probing the structure of this Mellin amplitude here. So it'll be very interesting to really just look at the structure, and look at for generic CFT, and look at how this limit behaves. For example, for n equals 4, you should be able to see just from the limit that
the Mellin amplitude should have this vanishing behavior by reading it off from the OB in this length and this length. And so this is, of course, this is something that is still ongoing and should be an interesting question to answer. Okay, so this is the end of the talk. Thank you.
Question?
There's something that in 3.5 minutes is getting disconnected. It will come.
Sorry, so ICTS, really sorry for all of this. Okay, so questions, ICTS? It's their problem. Yeah,
Hi, just a general question. So I thought Zohar and others also showed that there would have to be an infinite number of Regge trajectories, parallel Regge trajectories which are linear. Is that something you can see as well?
From the Mellin amplitude point of view, right now, no.
Yes.
What we can only see is that the JT has a linear region.
Okay.
Yeah.
Thank you.
Okay. TI part questions. I mean, Bombay questions.
So so when you look at the graviton scattering amplitude, the 4-point thing, so that implies something for the graviton massive 3-point function. Right. So now in an arbitrary theory, string theory, then massive are completely arbitrarily specifiable, or what? I mean, in principle, that's a new piece of information. What I mean to say is that no, I guess the answer is obviously yes. I mean, if I think of some kind of a string field theory, in which I'm sort of specifying all these 3-point vertices and trying to build a theory out of that. So then the 4-point function of the graviton vertices, they satisfy all kinds of good properties. But the 4-point function, if I
So you're asking if I just have some 4-point some massive 3-point interaction, and I'm starting to build my 4-point function.
yeah.
And of course, then in principle, it will not have any good high energy behavior. Is that the question?
Yeah,
And
yeah.
the question
the
is
first set of calculations about the 4 graviton amplitude does not say anything at all about the 4 massive particle, the 4 massive.
right. So you have to iteratively build up. So first, so after the 4 masses, you want to have 1 massive guy on the outside, or 2 massive guy. Then that builds up the 2 massive, 1 massive vertex. Once you have that under control, then of course you put the 2 massive on the outside, and then that gives you constraint on the 3 massive guys. So you iteratively build the constraints up.
You just change one of the external legs
Yeah.
by a massive particle, and
Two, actually, I think you need 2.
you need two.
Yeah.
But is it related at all in any which way to the Venetian family, to the Virasova amplitude? Right? If you have 2 gravitons and going to 2 massive particles, is it just some kind of a shift of the poles or something? Is it related to the?
Are you talking about within string theory or
String. Well, the question is more general, of course. But in general, the more general question is empty, because clearly I can specify the new 3-point functions any which way I want.
But then you would want good high energy behavior.
I want good high energy behavior
for all of them.
For all
Yeah.
of them.
So I think the problem is very likely to be very tight.
Yeah, it's very tight.
That my intuition would be that there are very few solutions.
As I mentioned, yeah, because again, you will have, in terms of just the functional form, you will have these infinite products which you have to satisfy these double poles, and the spectrum has to again match. Where now the spectrum is, because STU is not 0, everything is shifted a little bit, and then they still have to be consistent with the massless sector and so on and so forth. And so,
In fact, I think the problem gets much tighter. Because as he's shown, just the massless guy has solutions,
Yeah.
which are probably spurious. Where if the number of external particles is n, then you get n to the 4 equations. But the 3-point functions are just n cubed. Right, because it's nice. So as you take n to infinity, it sounds like you've got a very highly over-constrained problem.
But then with higher spins, the 3-point function for a given higher spin can have different, various, more and more complicated structures of that counting.
Without counting. This I agree. Okay. Yeah, that has to be taken. Let me ask a sort of general question. Suppose you took suppose we specialize to theories with large N theories, so conformal field theories with trace factorization. And we work with leading order in large N. Okay? For such theories, if I want to just reword the conformal field theory bootstrap equations in terms entirely of the Mellin amplitude. Okay? I'll get some set of conditions for the Mellin amplitudes of all 4-point functions. Because I'm focusing on large N theories, these should be sort of like conditions for classical scattering.
You're saying that the constraints I'm considering there's more constraints I can consider for them.
I just wanted to ask at the formal level whether every condition of the condition that you have a good conformal field theory can be reworded as well-defined constraints on these Mellin amplitudes. And I would imagine that that's a very hard or almost an empty problem for finite, but at large N, this should turn out to be sort of similar to the constraints that you have, as you mentioned, for just scattering amplitudes in flat space. Not just in some deformation of those rules that applies not just in funny high energy limits or Regge limits, but just always. So, okay, let me stop making statements, let me ask the question. The question is, can you just translate the rules of the conformal bootstrap for large N theories completely into rules for the Mellin amplitude, and thereby obtain a deformation of the scattering bootstrap that we have in flat space? For instance, in the limit that G goes to infinity, N goes to infinity with G held fixed, presumably this will really reduce to just the flat space bootstrap equation. Because then it's really, the bulk is really string theory in flat space. But away from that limit, it's not string theory in flat space, it's some deformation of those equations, I would imagine. So it sounds like this is defining an interesting deformation of the...
But that doesn't have anything to do with the flat space equations that we're going to solve.
So let me just, So I'm just regarding this as a way of solving conformal field theory.
Okay, I see.
Okay? This gives you some equations, but which may in some limit reduce to the usual Veneziano bootstrap equations. But in general should be a deformation of those equations. And I was wondering whether one could make that statement, precise.
Sorry, I can't answer that.
Okay. Actually, okay, go. I wanted to ask Rajesh if he had thought about this.
Yeah, I would agree, I think, in the sense that I think there's a whole family of string theories on ADS which would obey generalized criteria of the, so all of them probably have a flat space, large, many of them in the weak coupling limit would have a flat space limit, so there would be deformations of the Veneziano amplitude in some ways, and I think I think there should be a similar criterion that you can phrase for them as string theories and ADS, that they should satisfy similar positivity constraints, etc. But you could equivalently think of them as constraints on the dual conformal field theories at large N, which would be so they would the translation into the conformal field theory language would presumably be that they are valid solutions of the conformal bootstrap for the dual CFTs. Yes, I think this should be embedded as part of a larger larger story.
So in particular, does it sound reasonable that let me call the bootstrap equations of string theory from the 1960s that you've been looking at, basically. Let me call that the Veneziano bootstrap by abuse of history. Okay, so the Veneziano bootstrap is some set of equations on scattering amplitudes, which impose certain conditions, and we're familiar with that. But that should emerge as one end of a limit of constraint equations, which define conformal field theories. Do you think that sounds right?
That's what I was viewing this as, by thinking of flat space as a deformation or whatever, as an endpoint of string theories and ADS, varieties of string theories and ADS.
Yeah, so just formulating those equations in general sounds like an interesting thing in the sense that in flat space language and then as deformations of that. Sounds like an interesting thing. It's like a sharp connection between the flat space bootstrap and a deformation of the flat space bootstrap and the conformal bootstrap. Has this been done somewhere? In some language?
No, not explicitly, I think. Yeah. So, right. So in that sense, I think all large n solutions of the conformal bootstrap, all large n solutions satisfying certain properties of the conformal bootstrap should be should presumably have a limit which satisfies the Veneziano bootstrap. That's yeah, I think that's a reasonable conjecture, and
yeah. Okay, thanks. Okay, so no more questions, and thanks a lot, you two, for a very stimulating talk.
Thank you, everybody.